Good evening, my dear parents and dear students who are watching this program. Today we are going to have a very brand new session of the live classroom of the UAE. After a short break, we came back. So we are having sessions for grade 12 and a few sessions we had for grade 11. Today anyway, let us focus on some contents of grade 12 physics. So those who are watching this program, you may bring your notebook if you are a 12th standard science student, or if you are if you're a parent and your child is in grade 12, you insist him to watch this program today and request him to I request you to watch this till the end. So we'll have some questions to be worked out today, and today's live classroom I'm planning to divide into two segments. First segment, I'll brief you about certain contents of this chapter, which would help you to get into the content, and the second half will go for doing some numerical problems related to this chapter. So in between, if you have any confusions related to this chapter, if you want me to solve and show some questions, you can surely call and tell me which question you want me to solve. Watch this class carefully and make use of it. Of course, if any sort of difficulties in between, to catch up, you feel free to get back to us. So because it's a live session. It's a live classroom. You can see on the TV screen. It's a live class. So it's in fact it is the we may treat it as the biggest classroom of the UAE. Right. So let's straight away get into the contents of the chapter magnetism of grade 12. So in fact, magnetism basically arises due to the spin motion of electrons. That's a very basic thing we should have an idea about. Spin motion of electrons. But spinning electrons, we treat spinning electrons as an atomic magnet. We say it's a tiny magnet. But of course, if there are paired electrons, those atomic magnets will cancel off their effects. As a whole, there won't be any net magnetic effect, magnetic moment. So more precisely, we can say, according to molecular theory of magnetism, it is the spin motion of unpaired electrons magnetism arises. Okay, so that is the basic story behind magnetism. So now let's see what all contents we have in this chapter. We have I am talking about CBSE syllabus, chapter number 4. Okay, we have some laws to study. The Biot-Savart's law is there. Then we have Ampere's second law. Then we have the case of movement of a charged particle in a magnetic field. That is something which you have to really thorough with, because there are lots of questions, numerical problems, the concepts like cyclotron and all are there related to that. Then we have the fourth segment, which says the force acting on a current carrying conductor, which is again a small derivation we have, and based on that it follows with some other questions like force between two parallel wires carrying current, and also the torque acting on a current loop when placed inside a uniform magnetic field. Plus again we have application of that to moving coil galvanometer, and at the end of the chapter we have to learn the conversion of galvanometer into ammeter and voltmeter. These are the things which we have in this particular chapter. So one of the areas I want to focus today is the movement of charged particle in a magnetic field. When in an electric field, if a charged particle moves, it experiences a force, and that force, it's given by the equation F is equal to QE. F is equal to QE is the equation useful to calculate how much is the force experienced by a charged particle in the presence of an external electric field. So it simply shows that the charged particle, the experiences force, that force depends only on two factors, that is the charge and the strength of the electric field. That means as long as the charged particle is inside an electric field, the charge will experience force. That is, you just simply keep a charged particle inside the electric field. then what happens is the charged particle will be accelerated, it will gain speed, it will keep on gaining speed, right? It will gain kinetic energy, in other words. But in the case of charged particle in a magnetic field, the equation you should memorize is this one: F is equal to Q V B sin theta. But remember, that means unlike the force experienced by charged particle in an electric field, in magnetic field the force depends not only on the charge and the strength of the field, but it depends even on the velocity with which it is traveling and also the direction in which it is moving, that is how much angle it makes with the external magnetic field. That also is a factor. So that means there are 4 factors we can say on which the force experienced by charged particle in a magnetic field depends: the amount of charge, the strength of the field, the velocity with which it moves, and the direction in which it is moving. It means if a charged particle is simply like what we did in the electric field, if we simply keep a charged particle inside a magnetic field, like what we did in the electric field, okay, simply keep the charged particle in a magnetic field at rest, you know what will happen? Nothing will happen, it will remain there because there is no force on that. Again, a charged particle is moving in a magnetic field, so it has a velocity, right? But it is moving parallel to the field, let's say, that is making an angle 0 with the external magnetic field. Then also there won't be any force. That means simply a charged particle going through a region without any deflection it is going, you cannot simply say that there is no field or anything, there is no magnetic field. There may be a magnetic field, but that magnetic field is parallel to the velocity. That's the reason why it is not getting deflected, there is no force. So the force experienced by a charged particle will be in a magnetic field, will be there only if these conditions are not there, that is if it is at rest, no force; if it is moving parallel or even anti-parallel 180 degree as well, there is no force. Okay. In vector form, what else we can do is the same equation we can write it in vector form, that is Vb sin theta, you know it is V cross B. So Q multiplied by V cross B. Think of this, this is the vector form of the equation, right? So that means if it is an electric field, the vector form is like this, but in magnetic field this is the force. So you know we have studied a property of cross product. Velocity, magnetic field, cross product of these two is coming in this. You know what's the property we studied in cross product is, the cross product we are getting, right, that product is always perpendicular to both these vectors. That is, there are 2 vectors here. Here the vectors are velocity vector and magnetic field vector. So this, the force here, that is a cross product, can be considered as perpendicular to the velocity vector and even perpendicular to the magnetic field vector. So the 2 pairs that are perpendicular to each other are force and velocity, force and magnetic field. Now we think of this aspect, like if the charged particle is experiencing a force in a uniform magnetic field, okay, it experiences force in a uniform magnetic field, that force will always be perpendicular to the velocity. F and V are perpendicular. If force and velocity are perpendicular, can you say what exactly is happening when force and velocity are perpendicular? You might have studied in 11th standard, you studied a concept. Force is perpendicular to velocity. Can you say what's the concept where force is perpendicular to velocity? We have studied one concept, that is whenever a charged particle is moving in a circular path, this is the direction of force, and you know the tangent gives the direction of the velocity. So velocity is perpendicular to force. This force is the centripetal force. Centripetal force and velocity, these 2 vectors are perpendicular vectors. If they are perpendicular vectors, it simply means it is moving in a circular path. So what's the relevance over here? Here we have seen the velocity is always perpendicular to the force. Since velocity is perpendicular to force, charged particle moves in a circular path. That is the very important aspect of it. So in that case, we can say there are 2 or we can say otherwise 3 trajectories. So you can have a look at this, you just have a look at this video, okay, have a look at the screen. See, you can see a charged particle is present here. This is a positive charged particle, okay, this positive charged particle, I am going to release the positive charged particle. See, it's like this, it is going. Okay, when the charged particle is going towards the region, I set the magnetic field as 0, no magnetic field. So what happens? It is going without any deflection, right? Now, again, I am going to introduce a magnetic field. You can see this. See, some amount of magnetic field I am introducing here. Now the particle is moving. Just look at what is happening. Just carefully watch this. A positive charge particle is moving. You see, it is, see, I'll just pause it. What you can see over here is there is a perpendicular magnetic field. In the perpendicular magnetic field, the charge particle is moving in a circular path. But you see the two arrow marks. This arrow is what is indicating the direction of the force. This centripetal force. It is towards the center. Alright. And this is the direction of velocity. That is, it will go in a circular path. You see, a charged particle moving in a perpendicular magnetic field experiences a circular motion. That's the important aspect. Right? All of you have seen this. Right. Suppose if it is, I am going to change this to a negative charge. Okay. I'm going to change it to a negative charge. If it is a negative charge, you see what's happening. Again, charged particle is going through a magnetic field. Now the magnetic field is in such a way that it turns the other way. The direction of the force is reversed, or it is changed. Direction of force is in such a way that it will move in a circular path in this pattern. Why that is so? That is something which you have to explain now. Okay, I'll just show you once again. You just see, if I'm increasing the strength of the magnetic field, see just what is happening. I'm increasing the strength of the magnetic field and the negative charge particle is released. So as it is going through the magnetic field, see, now you can see that the charge particle goes in a smaller radius path. Okay, so what else you can make out is the vector, vector representing the force, that magnitude is increased. That is, there is a greater amount of force. This is what exactly happening when a charged particle is moving in a perpendicular magnetic field. Now I will just give you an idea about what is the reason for it. Okay, now we can have a look at this. So that is a charged particle when moving in a magnetic field. Suppose this is the magnetic field shown. Okay, this is the magnetic field. If the charged particle is going like this, and of course this is suppose it is a positive charge, right? Positive charge is moving in this way. Alright, if the charged particle is going like this, what is the direction of force? Actually, this direction of force by the field on the charged particle can be found with the help of Fleming's left hand rule. So you must be familiar with the Fleming's left hand rule, in which it says this finger, this finger represents the direction of magnetic field, this finger represents the direction of the current, then this will be the direction of the force. The three fingers, the Fleming's left hand rule. So here if you apply that, in the direction of current, what is the relevance here? The direction of current, here, but we are taking the case of charged particle moving. But of course, the movement of charged particle is what is giving rise to current. So what does that mean? It simply means if positive charge is going in this way, that itself is nothing but the direction of the current. Since if it was negative charge, suppose it was an electron, would have taken it in the opposite direction as the direction of current. Alright, so I am considering this as the direction of current, and you see this is the magnetic field. What you can make out, the thumb is upwards. So that means there is a force acting upwards. All of you understood this? This is direction of magnetic field into the plane, and this is the direction of current. Then thumb will indicate the direction of force. So that means if the charged particle is entering this way, it will move in a path in such a way that there will be force acting like this upwards. That is, it will go in a circular path like this. That's the reason why it turns into a circular path. Instead, if it was a negative charge, what would have been the picture? Just to see, this is a negative charge. Then what you should do is, this is magnetic field is this way, but current you should consider in the opposite direction to the flow of electrons. So look at the direction of thumb. Thumb is directed downwards. You see, that is, it will go this way. This is what exactly you have seen. If it was positive charge, it would be going like this. If it was negative charge, it would be going in this way. That you can make out with the help of Fleming's left hand rule. Okay, now again, if the charge particle, that means when a charge particle is going in a magnetic field, there are three possibilities of the trajectories. Three possibilities. One possibility is, let's just see, if the magnetic field is like this. The direction of magnetic field is from north to south, and in case if the charged particle goes this way, velocity is in that direction, the parallel to the magnetic field, let's say. Then what you can say about the force? The equation for the force we have got is QVB sine theta. So here what do you observe? There is no theta, theta is 0. That is sine 0 is 0. So there is no force. So what will you observe is it will go in a straight line. So this is one of the trajectories or the paths in which charged particle can move in a magnetic field. In a magnetic field, charged particle can go in a straight line path if it goes parallel to the field. Okay, that is the first situation. Second situation is what I described now already, that is if the charged particle is entering a perpendicular magnetic field like this, the magnetic field, and the velocity is this way, perpendicular magnetic field. So if it is going in a perpendicular magnetic field, just now we discussed about that only, if it is going in a perpendicular magnetic field, charged particle moves in a circular path because the full velocity is perpendicular to the force. If the force is perpendicular, velocity will go in a circular path. If it is going in a circular path, it will experience centripetal force. The centripetal force provided by the magnetic field is given by this equation, mv squared by r is equal to qvb. This will give you the value of radius of the trajectory, mv by qb. So you have to clearly understand this equation. It is very important to know this equation. There are many situations we make use of this one. So whenever you are given the case of charged particle entering a perpendicular magnetic field, you can use this equation, mv squared by r is equal to qvb, from which you will be able to reduce the equation to radius is equal to mv by qb. Okay. Now one more situation. So first situation is charge is going in a straight line if it is moving parallel or anti-parallel to the field. And second situation, if the charged particle is going perpendicular to the field, it goes in a circular path, circular. Okay. Now the third situation we will see. Third case is, that is if this is the magnetic field, okay, magnetic field lines are like this, but the charged particle enters this way. So the charged particle enters at an angle theta. Okay, with a velocity v it is going, and it enters at an angle theta with the field. If it is at an angle theta with the field, what else we can do is this velocity we may be able to resolve into two components. One component is v cos theta this way, that is the horizontal component, and this is v sin theta, that is the vertical component. So we have horizontal component and vertical component, right? Now what else is, we can treat this as the combination of the first and second situations. Okay, because there is a horizontal value of velocity, there is a vertical value or perpendicular component as well. Due to horizontal component, as we have discussed in the case of the first situation, due to horizontal component, what happens, the charged particle tend to go in a straight line, right, because there is no force because of the v cos theta. V cos theta does not contribute anything to the amount of force experienced by the charged particle, because v cos theta is parallel to the field. So the tendency of the charged particle is to go in a straight line. However, due to perpendicular component, that is v sin theta component, what happens, there will be circular motion, correct? That means, that is like in the second case. That means in the third situation is a combination of the first and second cases. That means the charged particle goes in a straight line and in a circular motion. How is that possible? That is, it is moving in a circular path, at the same time it is going in a straight line path also. That means goes like this, circular then straight line. Okay, it is moving ahead and it is going in a circular path as well. So that means the path or the trajectory of the charged particle can be drawn like this. Okay, so this is the pattern, what I call as that of a helix, right? That is, if the charged particle moves at an angle theta with the velocity, at an angle theta with the magnetic field, the path of the particle would be surely helical path, helix it is. But how do we measure a helix? Radius we used for measuring circular path, but helix, what's the way to measure? We measure helix by two ways, but two things we are going to measure with the help of or for helix. Okay, one is the radius, this one, this is the radius, and one more quantity we have associated with the helix is the what you call as pitch of the helix. Pitch and radius. How do you measure pitch and how do you measure radius? Radius we can measure with the make use of this itself, and you will be able to get the expression for radius. But remember, the velocity, the entire velocity is not used for the circular motion here, instead only a component which is the sine component. So we should use the equation r is equal to m v sin theta only by qb. So we will try this, we will use this equation, but instead of v you should use v sin theta, only v sin theta component. All of you understood that? In a circular path, in the third situation, when the particle is moving at an angle theta with the magnetic field, the horizontal component keeps the body moving in a circular path, whereas vertical component keeps the body in a keep the body move in a straight line path, whereas vertical component keeps the body move in a circular path. So straight line path and circular path together, combined effect is what is causing it to go in a helical path. But helix can be measured using its radius and using the pitch. What does pitch mean? Pitch would be like, when the charge particle is moving like this. So by the time it completes one revolution, how much it moves forward? That is the pitch. So pitch is the horizontal distance traveled by the charge particle during one complete revolution. So in fact, during one complete revolution means that revolution time, that time is what is called time period. Okay, so that you can calculate using the equation, the horizontal distance with the constant velocity. How do you calculate horizontal distance? It is just velocity times time. So which velocity is what is causing to go in a horizontal path? V cos theta multiplied by t. So this is what we discussed today. Now is a very important section, which is nothing but the movement of the charge particle in a magnetic field. Once again, let me tell you, when a charge particle enters a magnetic field, it can follow three different trajectories. There are three possibilities. First, if it is entering parallel to the field, simply the path will be straight line because it is not under any force. Second, if it is moving perpendicular to the field, it will go in a complete circular path whose radius can be calculated according to this equation. If it is moving in a, at an angle theta, that is at an arbitrary angle, the angle between 0 and 90 degree, if it is entering the field, since the velocity has two components, horizontal and vertical, horizontal component will make it to move in a straight line path, vertical component will make it to go in a circular path. So the combined effect will be that it will go, the charge particle follows a helical path. Okay, that helical path, the value of the helix or the measurement of the helix is radius and pitch, which you can calculate like this. Okay, at this point of time, I want to tell you one more thing, that is, in all these cases, let us think of how much work is imparted to the charge particle by the magnetic field. That is, charge particle is entering a magnetic field. When the charge particle is traveling into the field, how much work the field will do on the particle. To find it out, what you can do is, easy way is, you just think of this equation, one equation studied in 11th standard, if you remember. Power is equal to force dot V. Power is equal to force times dot product of force and velocity. This is power. Okay, power, force, F dot V. This is vector, dot product. Okay, so this, what does that mean? If the force is perpendicular to velocity, that is power, and power is generally we say power is a dot product of force and vector and velocity vector. Now you apply that situation in all these cases. What you can make out is, over here force is 0. If the force is 0, power is 0. If the power is 0, work done will be 0. Why? Because work done is, I will write it here, power is equal to work done by time, right? So if power is 0, work done will be 0. So what does it mean? In the first situation, since the force is 0, no work done. In the second situation, force is there, but that force is perpendicular to velocity. Force perpendicular to velocity, if two perpendicular vectors, the dot product is 0. So here also, since force is perpendicular to velocity, power is 0, therefore work done is 0. So second situation also, we find that work done is 0. How about the third situation? In the third situation, so in short, I can say third situation is a combination of first and second. First, what was the work? 0. Second, what was the work? 0. So third one also should be 0. Otherwise, we can say this way, in the third case, there is a force, but that force is not due to the entire velocity, only due to the perpendicular component. That perpendicular component is always perpendicular to the force as well, right? Therefore, no work done. And how about horizontal component? Horizontal component also is there, but it doesn't cause any force. So again, no work done. So the nutshell of this is, when a charge particle enters a magnetic field, the field doesn't do any work. The work done by the field on the charge particle is 0. So, in 11th grade one more concept is studied, that is work energy theorem. That is work done on a on a particle is simply change in its kinetic energy. So, here what will you observe? Magnetic field does not do any work. That means work done 0 means what? Change in kinetic energy is 0. If the change in kinetic energy is 0, what does it mean further? No change in kinetic energy, that is change in kinetic energy, otherwise the kinetic energy is constant. That is, whatever be the way the charged particle is going in a magnetic field, either a straight line or at an angle, whatever be the way the charged particle goes into a magnetic field, with some kinetic energy the charged particle enters the field, with the same amount of kinetic energy itself the charged particle will come out. Okay, so that is a very important aspect to understand. Magnetic field does not do any work on the charged particle. That means the charged particle does not gain any kinetic energy, or whatever kinetic energy initially it was possessing, with the same kinetic energy itself charged particle will come out of the magnetic field as well, come out of the magnetic field, that is without any change in kinetic energy it will come out. So, no change in kinetic energy when a charged particle is moving through a magnetic field. Okay. So, this concept of charged particle entering a perpendicular magnetic field is what is made use of in cyclotron. Now, one more point let me tell you. At the beginning I said the charged particle entering an electric field experiences force given by F is equal to QE. A charged particle entering a perpendicular magnetic field also will experience force given by F is equal to QVB. This is, let me consider the magnitudes. In a perpendicular magnetic field, this is the force. This is in an electric field. Okay. Now, let us think of the situation when the charged particle is entering a region where there is a combination of both electric field and magnetic field. Okay. So, then what will happen? That is something to understand first. So, that is, now I am going to explain the case when the charged particle enters a field, enters a region where there is a, we call it as a crossed electric and magnetic fields. Okay, such a region can be used to select the velocity of the charged particle. Okay, so I will explain it, this one, that is the concept of velocity selector. Okay, velocity selector or velocity filter we will do. I will show you some simulation based on this. So, after a short break we will come back and we will discuss the velocity selector, and of course we will do some numerical problems as well. So, those who are watching this program, stay tuned with this because we will be discussing some more extra aspects related to the same thing after a very short break. Okay.